So now that we understand Le Chatelier's principle a little bit more, what we can do is apply this to another equilibrium reaction that just looks a little bit different. A dissociation equation is actually an equilibrium reaction where we have equilibrium between the solid undissolved products and the dissolved ions in the solution. When it reaches a saturated state, that is actually the system at equilibrium. And so what we can do is apply Le Chatelier's principle to that as well in order to help us understand some effects. So to do this, we're going to take a look at some examples and see the effect of adding different substances to an equilibrium system using what we would call the common ion effect. So we're going to be working with this reaction for most of what we're going to do. And what we are going to have take place is we are going to manipulate this system by adding stresses. So we are going to add, very first of all, BaCl2. Now, it's important to understand that BaCl2 is actually made out of Ba2 plus and Cl minus. So what that means is there is a common ion. So what is going to take place when we add BaCl2 is there is going to be an increase in the amount of barium 2 plus dissolved in the solution. And this is our initial stress. When there is too much of a concentration of one product, equilibrium is going to shift to the left in response, right? We have too much of this stuff. That's going to speed up the reverse reaction, and it's actually going to increase the amount of barium sulfate in the solution. In order to do that, it actually had to use up the sulfate that was in there. So its concentration is going to go down. So by adding barium chloride, because of the common ion, we actually shift to the left. Now it's important to recognize that the state actually tells us that what's going on here is a precipitate is forming. By adding more of the barium into the solution, we cause barium sulfate to precipitate out. What we would say here is that the solubility of BaSO4 is going to decrease. And basically that's just a way of saying that it is going to precipitate out of the solution. So this is one example of how the ion effect, or the common ion effect, actually affects the solution. So let's do another example. So let's reset, and then we'll take a look at what happens when we add another substance. So now what we're going to do is we're going to be dealing with the same exact equation, but we're going to add Na2SO4. So again, think about what Na2SO4 is. Na2SO4 is actually sodium ions and sulfate ions. For us, this is the important one because there's a common ion. So that's going to increase the concentration of sulfate into this solution. Now, what is that actually going to do to the solution? Well, it's going to cause a shift to the left. You will precipitate barium sulfate. And in order to do that, you have to decrease the amount of barium in the solution as it combines together with the sulfate. Remember, you can't add to the left or to the right. You have to add to the whole thing. It's all in one beaker, in one container. So what happened to the solubility here? Well, the solubility is going to decrease because of the added sulfate causing the barium sulfate to precipitate. So the solubility goes down. Okay, so now that we've seen this example, let's try another one. This time we're going to add barium sulfate as a solid to this solution. Now, I would recommend right now pause and try and predict and see what's going to happen. chances are you probably thought, okay, that's going to increase barium sulfate. Don't copy this part down. Increase the barium sulfate, shift away, goes up, goes up, would be my guess, just from having done this a lot of times before. That is usually what people think. But keep in mind, this solution is already saturated. So it actually is not going to do anything. Adding more of that solid actually has no effect. So why does it have no effect? I think the best way to think about this is to think about dissolving a substance that you know. Think about making iced tea. You pour iced tea into a glass of water. You keep adding iced tea until you see a thick sludge at the bottom. At this point, if you pour more iced tea powder in, it's not going to dissolve. You're not going to be able to get more iced tea flavor out of what you've created. You're really just kind of wasting iced tea powder. And that principle is the exact same when it comes to barium sulfate or calcium chloride or any chemical substance. When it's saturated, adding more solid actually won't allow you to dissolve anymore because you've already dissolved the maximum amount that you possibly can. So a dissociation equation at equilibrium is a saturated solution. Adding more of the solid for that saturated solution will have no effect on the equilibrium. So now that we've seen that example of what happens when we add more of the solid substance, let's take a look at another example that's a little bit different. We're dealing with the same equation, but this time we're going to add H2O. I think you should probably pause again, try and predict, but this time before you pause, think about iced tea. Remember, barium sulfate follows the same rules as iced tea. So, pause and make your prediction. Hopefully what you realized is that adding more H2O actually decreases the concentration of the ions. You've added more solvent without adding more solute. So you've decreased the concentration of the ions in the solution. What that is going to do is it is going to shift equilibrium to the right. And it's going to decrease the amount of solid in the container by causing it to dissolve. Again, think about making iced tea. You've made your cup, you have a little bit of solid down in the bottom, you add more water. You can actually now dissolve the solid in the bottom because you've decreased the concentration of your iced tea. It probably tastes terrible right now because it's all watered down, but you could, if you wanted to, now dissolve a little bit more iced tea into it. You have shifted equilibrium by decreasing the concentration of the ions. So now that we've seen those examples, I have one more that's a little bit different. So again, let's take a look. So this time what we're going to do is we're going to have our solution, same as before, but we're going to add mercury ions. Now, maybe don't think about iced tea here. Don't put mercury in your iced tea. That's a terrible idea. Don't do that. That's going to kill you. But think about it here. Now, what you're probably realizing is there is no common ion. So you may think, well, there's no effect. But when we check our solubility table, what we see is that sulfate combined with mercury has low solubility. So what's actually going to happen here is the mercury ions in the solution that we just added are going to combine with the sulfate ions in the solution, and they're going to form into a solid mercury sulfate. When they do that, the sulfate in the solution is going to decrease in concentration. It's doing that because it's actually combining with the mercury and leaving the solution as a solid. So in order to respond to this stress, equilibrium shifts to the right. The concentration of barium goes up. The concentration of barium sulfate or the amount of barium sulfate solid is going to go down, so more will dissolve, and the solubility of barium sulfate has increased because you can now dissolve more. The common ion effect is really no different from Le Chatelier's principle. It's just taking a look at solubility rather than general equilibrium. So just be sure to apply those same principles and check for common ions. If there's no common ions, remember solids don't affect equilibrium. Adding water decreases concentrations, and adding a substance that doesn't have a common ion, you should probably check your solubility table and look to see if there's a precipitate. So thanks for watching, and I'll see you next time as we start doing calculations related to equilibrium.